Good morning, good afternoon, good evening for all of you joining. First, thank you so much to the India AMR Innovation Hub for asking me to speak on the occasion of World Antimicrobial Resistance Awareness Week. My name is Padmini Srikantiah. I am a Deputy Director in the Pneumonia Programs at the Bill and Melinda Gates Foundation in Seattle. And I also serve as the Foundation's Antimicrobial Resistance Strategy Lead. Our AMR strategy has a primary focus on prevention of mortality due to high-risk AMR pathogens in low and middle income country populations, and vaccines form a central part or pillar of that strategy. So today it's my pleasure to speak to you about the role of vaccines to reduce antimicrobial resistant pathogens. So as I think many of you have seen earlier this year in the report published in Lancet, the Global Antimicrobial Resistance Burden of Disease report, there are an estimated 4.9 million deaths associated with bacterial antimicrobial resistance globally in 2019. This makes this bacterial AMR the third underlying cause of disease in the global burden of disease level 3 causes, behind only ischemic heart disease and stroke. And with 1.3 or 1.27 million AMR attributable deaths, AMR is the 12th leading underlying cause of global burden of disease level 3 causes, which actually puts it ahead of HIV, TB, and malaria. Of course, many of you are also aware that the highest rates of deaths and the greatest number of burden of deaths are in low and middle income countries, which you can see on the figure here, where green is the regions in Africa and blue in South Asia. And those are the regions that are most directly and most significantly impacted. When we look at the top 6 pathogens responsible for the majority of these AMR attributable deaths, close to 1,929,000 deaths attributable to AMR, and over 3.5 million AMR deaths associated with AMR in 2019, there are 6 pathogens responsible for this: E. coli, Staph aureus, Klebsiella pneumoniae, Streptococcus pneumoniae, Acinetobacter baumannii, and Pseudomonas aeruginosa. Of these, there are only vaccines currently available for one of these pathogens, Streptococcus pneumoniae. And then if we include also the 7th pathogen, Mycobacterium tuberculosis, there's also a vaccine, long-standing vaccine available for TB, although of course there are ongoing efforts for more impactful vaccines. So we know and we see this great burden of disease due to this antimicrobial resistant pathogens. And we also see that there is great potential for vaccines that could target these pathogens to help reduce these AMR deaths, as well as reduce antimicrobial resistance and antibiotic use. And why do we actually center so much of our strategy on vaccines rather than focusing on new antimicrobials, while acknowledging absolutely that the need for new and efficacious antimicrobials is paramount and important in the fight against antimicrobial resistance? We see that the time between deployment between the first documented use of a vaccine versus an antimicrobial to the first documented resistance in humans due to resistance is much, much longer in vaccines compared to antibiotics. So while we know that there will be infections due to multi-drug resistant organisms that will require new and efficacious vaccine antimicrobials, as well as more judicious and appropriate use of existing antibiotics, we see that the use of vaccines has a longevity that is hard to beat. And that's part of the reason that we at the Foundation are placing such importance on the potential of vaccines to address AMR. So I'm going to go back to March of 2017, where there was a meeting at the Chatham House on the value of vaccines for antimicrobial resistance. And in this meeting, there was a clear understanding and discussion about the potential that vaccines can play to address antimicrobial resistance. But unlike the attention that had been given to prioritizing pathogens for new antibiotic development for AMR, there wasn't an equivalent list for a vaccine priority list. So many of the questions that came about were, how should the value of vaccines be attributed in the context of antimicrobial resistance? There was a clear need articulated to model that impact of vaccines on antimicrobial resistance and key pathogens that were actually discussed. Many of them, including tuberculosis, Staph aureus, Pseudomonas, and Klebsiella, are in the top 6 pathogens that were outlined in the global burden of disease estimates. But there are also other pathogens for which resistance in and of itself may not be a huge issue, such as strep pyogenes, or even viral pathogens such as influenza and RSV, but that antimicrobial use actually is a huge component of what drives treatment for these pathogens. And vaccines for these pathogens might have an impact on indiscriminate antimicrobial use. So we actually thereafter have, at the foundation, developed 2 different partnerships. One with WHO to really support the establishment of an initiative on vaccines to address AMR at the World Health Organization, and to help prioritize and develop a vaccine attributable framework for AMR. In addition, we have supported the Center for Disease Dynamics and Economic Policy, which is now known as the One Health Trust, to form a consortium of modelers that they called ARVAC, or Antimicrobial Resistance and Vaccines Modeling Consortium, to quantify the potential impact of vaccines against antimicrobial resistance for a number of pathogens. So subsequently, we have seen in the last couple of years, after our initial engagement with WHO in 2018, that WHO in 2020 came out with an action framework on vaccines to address AMR. And on this pictorial on the right, you can see this nice graphic that shows that vaccines, of course, protect individuals directly, but they can also decrease infections overall by their herd immunity potential in some pathogens, as well as reduce the incidence of resistant pathogens or resistant disease. And this subsequently can lead to the decreased use of antimicrobials and suppress resistance evolution, which both can allow decreased risk at the individual levels and enable antibiotics to be used effectively for longer. In addition, we know that some of these vaccines can also help reduce secondary infections, particularly those for viral pathogens where secondary bacterial infections may be a significant concern. So within the next 20 or so minutes, I'll be focusing on a number of pathogens and data. And strategically, the framework that we're using is the impact on both AMR burden as well as antibiotic use is demonstrable for existing vaccines that target AMR bacterial pathogens. So this includes pneumococcal conjugate vaccine, for which I'll share some data, and more recently, typhoid conjugate vaccine on resistant Salmonella typhi, and in the case of pneumococcus, penicillin non-susceptible Streptococcus pneumoniae. Vaccines may also reduce bacterial infections where resistance is not major, but that they may drive antibiotic use, significant antibiotic use, such as with group B Streptococcus, where there is widespread intrapartum antibiotic prophylaxis, as well as group A Streptococcus, where if a vaccine could be made, could reduce antibiotic use for skin and throat infections. I will not be sharing too much data on these 2 vaccines, but I will, however, also focus on the impact on antibiotic use of existing viral vaccines, measles, influenza, rotavirus, and then now RSV, for which we have some data from clinical trials, and now finally have some compelling data that are coming out for hopeful licensure of an RSV vaccine in the next year or 2. And finally, I'll talk about new vaccines that could be developed to combat key AMR pathogens, focusing on Klebsiella pneumoniae, and in particular, the prospect of maternal immunization that could prevent and protect neonatal sepsis, or prevent neonatal sepsis and protect neonates in the first few months of life. So let's start looking at the data. So when we look at pneumococcal conjugate vaccine, I'll first look at data from the United States. And here is a paper from 2006 in the New England Journal, which showed that showed a clear reduction in pneumococcal invasive pneumococcal disease due to penicillin non-susceptible strains after the introduction of pneumococcal conjugate vaccine. So on the figure on the left, when the vaccine was introduced in 2000, there was both penicillin susceptible disease as well as penicillin non-susceptible disease, shown respectively in pink and blue. And you can see very clearly this sharp decline in both penicillin susceptible and non-susceptible disease among children who are vaccinated under 2 years of age between 1996 to 2004. When we look at the figure on the right, we actually see that even though there was vaccination for pneumococcal conjugate vaccine in young children and young infants, there was a broader herd impact, including that seen very strikingly in those of older age, and in particular in purple in those greater than 65 years of age, where penicillin non-susceptible pneumococci started to decrease after the introduction of a pneumococcal conjugate vaccine in young infants, even in other age groups that have been significantly impacted previously. Data from California also showed this reduction in antibiotic use in the pneumococcal conjugate vaccine PCV7 trial, where antibiotic prescriptions were reduced by 5% in all follow-ups starting at dose 1, and by almost 6% after the primary series. And PCV reduced the subset of second-line antibiotics by about 12% in all-time follow-up and 13% in the per-protocol follow-up. So in total, PCV prevented a total of 35 antibiotic prescriptions per 100 children vaccinated per protocol, which is quite a significant finding. A similar analysis in Finland also showed that in an assessment of vaccine effectiveness against outpatient prescriptions of antimicrobial drugs recommended by the National Treatment Guidelines for acute otitis media in Finland in children who had received at least 1 dose of the study vaccine before 7 months of age. And what you see is actually in the figure on the left, a percentage, the vaccine effectiveness of the vaccine to reduce antimicrobial prescriptions by episode and by age group. And while the overall vaccine impact was on the range of 8 to about 15%, this result actually, because of the overall incidence of antimicrobial prescriptions and the overall incidence of these sorts of otitis episodes, this reduction would lead to over 12,000 fewer antimicrobial purchases per year in children less than 24 months in Finland. So we see these significant data both from the United States as well as Finland on pneumococcal conjugate vaccine. What about in other geographies outside the global north? So the pneumococcal conjugate vaccine was introduced in South Africa some years later in about 2008 or so. And in South Africa, PCV and P10 as well as PCV13 reintroduction was associated with an 82% reduction in penicillin-resistant invasive pneumococcal disease in children, and an 85% reduction in ceftriaxone non-susceptible strains. So we see similar trends in very different geographies. And similarly, the introduction of PCV was associated with a reduction in antibiotic use due to the decrease in pneumococcal infections in and of themselves. More recently, one of the analyses through the ARVac consortium looked at the potential impact, the impact of PCV as well as rotavirus vaccines on antimicrobial use, focusing on low and middle income countries. And if we look at the figure on the left, the top half of the figure is focused on antibiotic treatment of respiratory infections, and the bottom half on antibiotic treatment of diarrhea. And what we see is on the left is a no vaccination scenario, and we see the incidence of antibiotic treatment of respiratory infections in the blue figure, and looking at low, middle, and upper middle income countries, and all LMICs in blue. In comparison, when we look at the number of antibiotic treated illnesses prevented under the current coverage rates in children under 5 for pneumococcal conjugate vaccine, we see that there's almost 24 million illnesses, antibiotic treatment illnesses, that have been prevented under the current 2018 coverage rates in children under 5 due to pneumococcal conjugate vaccine. If you then look at the final figure on the right half of the top part of the graphic, if we were to further expand coverage to pneumococcal conjugate vaccine to true universal coverage, that coverage would further decrease the incidence and the number, rather, of antibiotic treated illnesses in these low and middle income country geographies. So on the left in blue is the incidence, and on the right in purple is the estimated total number of cases. If we shift our attention to the bottom half of the graphic, to antibiotic treatment of diarrhea, again, in a no vaccination scenario, you see the incidence of over 10 per 100 children, very frequent incidence of diarrheal illness. But if you look at the total number of cases of antibiotic treated diarrhea, in a no vaccination scenario, there's compared to a vaccinated scenario of current coverage, there's a reduction in 13.6 million antibiotic treated diarrheal episodes that can be associated or related to rotavirus coverage, rotavirus vaccine coverage. And again, if we expand this coverage to true universal coverage, this modeling estimate suggests an even further reduction in antibiotic treated illnesses. And indeed, what they estimate is direct protection resulting from the achievement of universal vaccine coverage targets for these vaccines could prevent an additional 40 million episodes of antibiotic treated illness. So the data that we saw initially on pneumococcal conjugate vaccines focusing on higher income countries clearly translated in South Africa to lower and low middle income country geographies. And then this broader analysis of antibiotic treated illnesses across low middle income geographies appears to underscore these very findings. If we shift now from rotavirus now to typhoid fever, what we see on the left is the percentage of fluoroquinolone non-susceptible cases of typhoid fever that would be that are currently affecting the globe. And geographically, you see that this burden of disease is very much concentrated in sub-Saharan Africa and South Asia and Southeast Asia. And on the bottom is the percentage of multi-drug resistant cases of typhoid fever as well. Similar geographies that have been affected. In the after the introduction of a typhoid conjugate vaccine in these geographies, what these investigators from Yale University and a consortium of other investigators estimate is the percentage of fluoroquinolone non-susceptible cases of typhoid fever that would be averted. And you see that across the board in multiple countries, this percentage of cases that could be averted due to the introduction of typhoid conjugate vaccine exceeds 50% in most of these geographies. And this is similarly seen for the percentage of multi-drug resistant cases of typhoid fever that also would be averted in the introduction of a typhoid conjugate vaccine. What remains to be seen and what needs to be followed up now is how do we actually measure the reduction, and do we see a significant reduction in antibiotic use that are concurrent with these reductions or estimated and anticipated reductions in drug-resistant and multi-drug resistant typhoid fever. Let's shift now from thinking about these bacterial pathogens for which there are vaccines to actually broadening our scope to look at viruses. So when we think about AMR, of course, our primary concern becomes bacterial AMR. But antibiotic use is not driven solely by bacterial infections. And we know that viral infections, especially respiratory viral infections, can readily cause and lead to antibiotic prescriptions, in addition to the example of rotavirus that we've just recently discussed. So when we look at universal influenza vaccine programs and the potential impact of influenza vaccination on antibiotic prescriptions, a great example is the universal influenza vaccination program in Ontario province of Canada. So in 2000, Ontario province introduced free universal seasonal influenza vaccination. And what they did was compared the rates of respiratory antibiotic prescriptions before and after this universal influenza vaccination program in Ontario province compared to other provinces where there was influenza vaccination available, but it was not free universal influenza vaccination like it was in Ontario. And what you see very, very dramatically here is a 64% reduction in antibiotic prescriptions compared to the other provinces. And if the influenza was prevented, we know that there's also a decreased likelihood of secondary bacterial infections, including bacterial pneumonia, as well as otitis media. And we see this concomitant reduction in antibiotic prescriptions and antibiotic use. A similar analysis of influenza vaccine on antibiotic use was conducted and looking at actually the mean number of antibiotic courses given to children. So if the Ontario example was focused on the whole population, this analysis from Finland is looking at influenza vaccination in a comparison of a history of recurrent otitis media during the 6-month study period. And what they see here, again, is a 13% vaccine effectiveness just against antibiotic courses prescribed among those who were vaccinated compared to those in the control arm who had not received a vaccine for acute otitis media. So we know not only are we reducing influenza, but we're also seeing a reduction in these secondary bacterial infections and therefore seeing a reduction in antimicrobial use. If we shift our attention from influenza to actually measles vaccine, we don't often think of AMR and measles in the same sentence, but there have been older data actually looking at the association between earlier measles vaccine given at 6 months versus 9 months and subsequent antibiotic treatment. And those who had early measles vaccine had a reduction again in antibiotic treatment for early versus those who did not receive early measles vaccination. So this is another example of an existing vaccine where we don't often expand and think about existing vaccination programs and how improving coverage or even modifying the vaccine schedule could impact AMR and antibiotic use and antibiotic prescriptions. And then a more recent example. So in 2019, the company Novavax had released their findings of their phase 3 pivotal maternal RSV vaccine trial. So RSV, or respiratory syncytial virus, is the most common cause of lower respiratory tract infection globally, particularly in young infants, especially those in 6 months, those 6 months or younger. So the RSV vaccine was a maternal vaccine given to pregnant mothers between 28 and 36 weeks of gestational age, and was intended to provide passive immunity to their newborn infants through 90 days or out through 6 months of life. And while the vaccine itself did not meet its primary endpoint to then move on to achieve licensure, the vaccine did show about 40% reduction in medically attended RSV, lower respiratory tract infection, particularly seen in the first 90 days of life. What the ARVAC consortium then did is, using the trial data from Novavax, who had also collected meticulously the antibiotic use in infants in the control and placebo arms of the trial, looked at the impact on antibiotic use in vaccine versus placebo arm. And you see again here that even in a vaccine that had modest to moderate efficacy, a 13% vaccine efficacy against reduction of antibiotic prescriptions in the first 90 days of life. And when they looked for all-cause antimicrobial prescriptions, and when they looked more closely at antimicrobial prescriptions for lower respiratory tract infections, indeed they saw this 16% reduction in antimicrobial use in the vaccine compared to the placebo arm. The investigators further looked at high-income settings, seen on the figure on the right and outlined in red, compared to low middle-income country settings in the first 90 days of life, and looked at the number of LRTI-associated antibiotic courses averted per 100 infants. And you see that there's an impact seen in high-income countries and an association seen in low-income countries, although indeed that confidence interval does cross 0. But if we look specifically at the first 90 days of life for all antibiotics given, even in low and middle-income countries, we do see this reduction in LRTI antibiotic-associated courses. And in particular, this impact is seen in low middle-income countries for antibiotics like cephalosporins, which are indeed at risk of overuse and resistance. So an impact seen in both low-income countries and high-income countries. And subsequent to this, we have seen more recent data from an RSV infant long-acting monoclonal antibody trial, nirsevimab, who recently released their phase 3 data and actually combined analysis of their phase 2 and phase 3 data, which similarly showed a reduction of about 20% in antimicrobial prescriptions in the intervention versus placebo arms for an RSV infant monoclonal antibody that showed an efficacy of 75% to reduce RSV disease. So we anticipate that as we see more efficacious RSV prevention products coming forward, we will hopefully see the similar trend of an impact on all-cause LRTI as well as antibiotic prescriptions and use, both in high and low-income countries. I want to shift now from vaccines that exist, like those we discussed for pneumococcus and typhoid, as well as viral vaccines that exist for rotavirus, influenza, and very late stage vaccines in clinical development for RSV, to pathogens that are of high concern for antimicrobial resistance, for which we don't yet have vaccines. And first, I want to turn to some of the surveillance data. So if we look specifically in sub-Saharan Africa, and these trends are repeated, of course, in South Asia, we see that antimicrobial resistance is increasingly seen in neonatal sepsis as a particular population of concern that are disproportionately impacted by multi-drug resistant pathogens. So in this systematic review and meta-analysis of neonatal sepsis in sub-Saharan Africa, the investigators looked at over 150 studies representing over 84,000 neonates from 26 countries and compared two different periods, an earlier period from 1980 to 2007 to a later period from 2008 to 2018. There were 70 studies with blood culture data, and the majority of the studies were from urban tertiary facilities. And what you see in gram-positive organisms, not surprisingly, Staph aureus and group B streptococcus as the leading etiologies, and in gram-negative sepsis, Klebsiella and E. coli. What is also striking is that resistance is much more, was evaluated in the later time period, and we see a high prevalence of resistance to beta-lactams, 68%, a high resistance to aminoglycosides, and we know that these trends are actually replicated in and even more striking in South Asia, where not only do we see a resistance to beta-lactams, but actually increased resistance to cephalosporins and even to carbapenems. So we know we are dealing with a global epidemic of multi-drug resistant gram-negative sepsis in neonates that is associated with an excess of mortality. Of the organisms, the one that seems to be leading the pack consistently across geographies is Klebsiella pneumoniae, and these are data from the GARD-PES neonatal observational cohort study conducted in over 13 countries and almost 20 sites, which included sites in India as well. That Klebsiella pneumoniae was the leading etiology of neonatal sepsis and related deaths after the first 24 hours of life, and was indeed associated with a high mortality, over 20%, and that compared to other organisms and when no organism was detected. In other surveillance platforms, including the Child Health and Mortality Prevention Surveillance platform that we at the Foundation support, looking at etiologies of death in children under 5, Klebsiella pneumoniae accounts for over 40% of infectious deaths in neonates in the first, in between days 2 and 28 of life. And so this is why at the Foundation, we have now prioritized Klebsiella pneumoniae as a vaccine of interest for a vaccine development strategy. And in particular, again, given the preponderance of infections we're seeing in neonates, we're targeting a maternal vaccine strategy. And so here we're looking at Klebsiella pneumoniae's capsular and subcapsular antigens, of which there are over 77 capsular antigens and over 8 distinct subcapsular O antigens. And our early vaccine discovery strategy is now trying to understand the seroepidemiology of capsular and subcapsular antigens in neonatal sepsis in low and middle income country geographies to then inform our vaccine immunogen design, which we anticipate being a high valency conjugate vaccine approach. Of course, we're still very early in our Klebsiella vaccine development strategy, and we will need to first demonstrate that antibodies targeting these capsular antigens can indeed confer protection in a maternal immunization model, which is what we're working on over the next, currently and over the next 12 to 18 months, we hope to generate these data. But this just shows that even for these high priority AMR pathogens, like the 6 pathogens that are associated with close to 1 million AMR attributable deaths, there is a prospect of thinking about vaccine strategies that could potentially impact both a resistance as well as, of course, what's driving our overall interest, which is reducing mortality. So what we are currently investing in is, again, as I said, a WHO technical roadmap that now expresses priority actions aimed to strengthen the role of vaccines against AMR. This includes evidence generation, systematically incorporating AMR reduction into decision-making for currently available vaccines, as well as future vaccines, and systematically incorporating the estimation of vaccine impact into decision-making for AMR control strategies. So this is really a crosstalk between the vaccine decision makers and those who are actually focused on antimicrobial resistance, and recognizing in both arenas that vaccines can play a role for AMR, and AMR should really be part of decision-making for vaccine policy and vaccine development decisions. WHO, as I mentioned, should be coming out soon with this vaccine value attribution framework to prioritize vaccines for AMR, which would support decisions both at the vaccine development stage as well as the vaccines use stage. And importantly, the scope of this value attribution framework goes beyond the WHO AMR priority list of pathogens to include additional bacteria as well as viruses for which vaccines, as we saw earlier, can have an impact on antibiotic use and ideally, ultimately resistance. And as I mentioned, we have had this partnership, very productive partnership with the One Health Trust, who through their consortium have estimated and quantified the potential impact of vaccines on antimicrobial resistance for a number of pathogens, some of the data of which I shared earlier in the presentation. And what we're moving to now is a partnership with the One Health Trust that is now shifting the data from a global level to moving towards advocacy at the country level and focusing on 12 low and middle income countries where the data on vaccines and AMR can be focused more at the country level to bring forward the decision makers, both in the AMR as well as immunization policy circles, such that these data become the genesis of more fruitful discussions about how AMR can guide vaccine policy decisions and how vaccines can be incorporated into antimicrobial resistance national action plans. And on that note, when we look at, and then this slide is courtesy of our colleague at WHO, when we look at vaccines that and how vaccines are included in AMR national action plans, an analysis conducted by a group called Nivelle in the Netherlands looked at 77 national action plans to measure how many of these plans actually mention vaccines. And it's about 87% that mention vaccines, but only 43%, 43% have developed indicators to capture the role of vaccines against AMR, and 10 national action plans don't mention vaccines at all. We do know that that in the guidance from WHO on global guidance on national action plans for prevention of AMR, immunization coverage, and targeting some key priority vaccines, including pneumococcal conjugate vaccines, rotavirus, and measles-containing vaccines, for which we saw data on impact on antibiotic use earlier, are included as key targets for immunization agendas, but also can be included in AMR national action plans. So there is definitely room for improvement in how we consider vaccines in as a tool in the AMR circles themselves. So in summary, I want to say that vaccines, we believe at the Foundation, vaccines are a central pillar and really have much to contribute to the fight against antimicrobial resistance. Current vaccines like pneumococcal conjugate vaccine and typhoid conjugate vaccine have been shown or are projected to show a reduction in both antibiotic-resistant infections as well as antibiotic use. Viral vaccines, such as those to prevent influenza, rotavirus, and RSV, have all been demonstrated to reduce antimicrobial use, and this should be part of the decision-making process for whether these vaccines make sense for introduction in a country by vaccine policymakers, and the impact of these viral vaccines on antimicrobial use should be taken into account by AMR policy and decision makers. Vaccines against largely susceptible bacterial pathogens like Group B strep and Group A strep, which we didn't talk about in detail in this talk, are also have potential to reduce antibiotic use. And we clearly need progress for key AMR pathogens. I highlighted Klebsiella, but others, including tuberculosis, Staphylococcus aureus, and gonococci, are high on the list of priority for vaccine development that have potential to address and reduce resistant pathogens as well as antimicrobial use. The cost benefit of a focus on vaccines to reduce antimicrobial resistance is also a key priority for WHO, as we know that countries, when they're making decisions for their AMR national action plans, will have to weigh the relative cost benefit of vaccines versus other approaches, including stewardship in infection prevention and control. And we would hope that the pie is large enough to support all of these important prevention agendas. So with that, I would like to thank you very much for inviting me to speak and share our thoughts with you. and for your attention. I want to acknowledge my colleagues at the Gates Foundation, in particular Keith Plugman, who leads the pneumonia team and is my director, as well as our deputy directors in our pneumonia team, Kristen Savage, as well as key colleagues at the One Health Trust, directed by Ramanan Lakshminarayan, and at the WHO in the immunizations, vaccines, and biologics group, Matthias Hasso-Agopsowitz, who is leading a lot of the AMR and vaccines work. And of course, and not on this slide, but our AMR colleagues at WHO as well. Thank you once again for your attention, and we hope to continue this dialogue on the importance of vaccines to address AMR. Thank you.